everyone, my name is Lisa Worston, and today we're going to be talking about eccentricity. If you remember from the beginning of the course, eccentricity is basically calculating the out of roundness that the orbit of a planet may have. So eccentricity has values ranging from 0 to 1, 0 being a planet having a circular orbit, and 1 being a planet having a more straight line-like orbit. The more eccentric you are, the more oval-like shape or elliptical your orbit may be. And the closer to 0 you would be, the more circular your orbit would be. So today I'm going to teach you how to do this measuring eccentricity at home. So what I have is a blank sheet of paper on top of a piece of corkboard. What I'm going to do is first take a ruler, my pencil, and measure the distance roughly halfway through the page lengthwise. So I'm just going to set my paper down, place my ruler on where I think the center is, and draw a straight line across. This is going to be the basis from the length of the major axes for the ellipse that I'm going to draw. So now I have my paper with my line roughly halfway across, and what I'm going to do now is take 2 thumbtacks, which are going to act as my foci. I'm going to take the first thumbtack and I'm going to place it near the center of the page, right on the line. I'm not placing the thumbtack all the way down because I need a string to fit between the thumbtack and the corkboard. Next what I'm going to do is put a second thumbtack, and I'm going to measure it 3 centimeters away from the center thumbtack. So again, I'm going to put my paper down for a second. I'm going to take my ruler and measure in centimeters, 3 centimeters away from the center, and place the second thumbtack on that point. So now I have my 2 foci points that are now 3 centimeters apart from each other, and I have a piece of string that I recently tied together, which is going to help me draw the shape of my ellipse. I'm going to take my string, place it on top of my thumbtacks, take my pencil, and I'm going to carefully put my pencil over the string and gently pull along the thumbtacks, drawing the shape of this ellipse. Sometimes the pencil comes away from the string, so you just have to step back and try it again. Okay, so I can take my string off now. And as you can see, the shape of this ellipse looks fairly circular. However, it is not circular, otherwise we would have these 2 thumbtacks on top of each other, as you're going to see in a little while. So what I'm going to do is take my pencil, and I'm going to label this ellipse number 1 because I'm going to end up drawing 3 shapes, and I don't want to get them confused. Now, in order to calculate eccentricity, I'm going to put my calculation at the top of the page. Eccentricity equals distance between foci divided by the length of the major axes, which would be from one point of the ellipse to the other points going lengthwise across. So I already mentioned that I measured 3 centimeters between my foci points. So 3 centimeters will be on my numerator. For my denominator, I need to measure the length of the major axes. So I'm going to take my ruler in centimeters and measure from point A to point B across my ellipse lengthwise. And it looks like the length of the major axis is 15.2 centimeters. That number goes on my denominator. Now, to calculate eccentricity, I'm going to take my calculator and I'm going to divide 3 by 15.2. And it looks like my eccentricity for this ellipse is 0.197. So that basically concludes that the shape of this orbit is fairly close to 0, however it's not a perfect 0, so it's not a perfect circle. However, it has a more circular shape. Let's take a look and do ellipse number 2. So what I'm going to do is keep my first thumbtack in the center. I'm going to take my second thumbtack out and measure 3 new centimeters away from that point. So I'm going to take my ruler, put it on the point that it was on before, and I'm going to measure 3 centimeters away further. I'm going to put the thumbtack on that new spot. Okay, so now my 2 foci points are even further apart. Now they're about 6 centimeters apart. So to draw the second ellipse, I'm going to take my string, place it over the 2 thumbtacks again, take my pencil, densely pull along the string, and kind of let it guide me drawing the new shape of this ellipse. Okay, and take my string away. And if you see, the shape of my second ellipse is a little bit smaller and it's also more oval-like. So the further you move your two foci points away from each other, the more eccentric that orbit should be. So let's take a look at that. Let's do a new calculation. So eccentricity is now going to equal distance between foci, which is now 6 centimeters, because I moved it 3 centimeters away a second time, divided by the length of major axes. So I need to remeasure this new ellipse. And that looks to be about 12.1 centimeters. So if I take my calculator and now I'm going to divide 6 by 12.1, my eccentricity for ellipse number 2 is 0.496. 0.496. So you can see that 0.496 is roughly halfway between 0 and 1, so we are definitely getting more eccentric or oval-like rather than circular. I want to do one more thing with you guys and show you what a perfect circular orbit would be. So if we had a perfect circular orbit, we would have an eccentricity of 0, which means that the distance between foci would be 0. So if I were to take my second thumbtack and put it on top of the first one, we would have no distance between them. Since I can't put two thumbtacks on top of each other, I'm just going to take one away and draw the new shape. I'm going to take my string, my pencil, around the string, and draw a new shape. Okay. If you see, what I drew now is the outer line, and this is a perfectly circular orbit. It looks a lot more circular than the first or second ellipses did. So, to calculate the eccentricity of shape number 3, distance between foci is now 0, because if we had two foci on top of each other, there would be no distance between them. So 0 centimeters goes on the top. I do, though, need to measure my length of the major axes. So for this circle, I'm going to measure all the way across, and it looks like exactly 18 centimeters. So 0 centimeters divided by 18 is going to be 0.000, because 0 is going to the 1,000. So we have a perfectly circular orbit. That's how to do an easy calculation at home, but if you want to compare your numbers to the actual eccentricities of the planets, what I have is a chart called the Solar System Data Chart. I'm just going to hold this up for you guys. What you can see looking at the 5th column are eccentricities of planets. And one thing I want to point out that's kind of a misconception, there is no relationship between distance from the sun and eccentricity. And what I mean by that is, some people happen to think that the further you go from the sun, the more eccentric your orbit will be, or the more oval-like it will be, but that is a misconception. If you notice, looking at column number 5, there is no relationship between the planet's distance from the sun and its eccentricity. Mercury, which is actually the closest planet, has the largest eccentricity of 0.206. Earth, which is actually the third planet in, has an eccentricity of 0.017. So there is no relationship between distance from the sun and eccentricity. And if you look all the way down to Neptune, all of the numbers are in a random pattern. That concludes our lesson from today. I just want to point out that I have 3 sources that I use to do my project, which would be regentsearthscience.org, NASA's EarthObservatory.com, and www.enchantedlearning.com. I hope you guys enjoyed the lesson and learned something fun about eccentricity.